So sampling distribution. Remember, you have a normal distribution with some mu and sigma squared. Got a good marker. Then we have a random sample. By the way, what was the definition of random sample? What was it? Random sample is IID, independently identically distributed. Exactly. So we have IID sample, and we apply a function. Let's say x bar. We want to know what is the distribution of x bar, and we call this sampling distribution. Okay? And if the variance is known, like this, if we know the value of sigma squared, then I can say x bar follows a normal distribution with this mu and this variance, and therefore I can standardize it to standard normal. For two populations, again the same thing. The difference follows a basically normal distribution, and I can standardize it. The main assumption, though, here is x1, or the sample from the first population and the sample from second population are independent. Okay? So that's basically the distribution for the difference of sample averages. Okay? Difference of why it's not working. You see it? Yeah. So difference of sample averages here. Okay. Then we said, what if we want to know the distribution of S squared? And we said, okay, that distribution can be defined using chi-square distribution if we have some multiplier. So n minus 1, which is the sample size, minus 1, divided by sigma squared times S squared. That quantity follows a chi-square distribution with n minus 1 degrees of freedom. We had a couple of examples. And in one example, we saw that if we have chi-square distribution with 2 degrees of freedom, then it becomes what? It becomes, remember, exponential distribution with lambda equal to 0.5. Okay. So what if we have, any questions so far? What if we have one population, the variance is unknown, and we want to know what is the distribution of x bar? So in this case, we say the standardized version of x bar, when we use S instead of sigma, follows a t distribution with n minus 1 degrees of freedom. And we show that like how this is related to the definition of a t distribution, which is z divided by a square root of a chi-square divided by degrees of freedom. We use that definition, and we could derive something like this. Remember? And we had again one example. We used table for that, and I think we stopped here. So any questions so far? One population, two population, x bar 1 minus x bar 2, known mean, known variance, unknown variance? Nope. No questions? Okay, let's see. So for two populations, so let's say we have two populations. One is x1, 1 up to x, I don't know how did I call them? Yeah, x1 up to xn1. The other population is, let's say this is the second population. This is mu1, sigma 1. Again is normal, mu2, sigma 2. And we have y1 up to yn2. And we can find y bar here. Okay? Now, I guess I need to use this one. So, variances in this case are unknown. But I have one important assumption. Although they are unknown, they have the same variance. Okay? So variance are the same, equal to a quantity which I don't know. Okay? So what should I do? I need to estimate that. Okay? Do you remember, I think, I don't think I have discussed this, but anyways, so our x bar and y bar, we know that individually, in this case, they follow a t distribution. Now we want to know what would be the distribution of x bar minus y bar. Okay? When we don't know the variances, but they are equal. So we can say in this case, if I standardize it, again, can you see this or not? Nope.
Can you lower this arm thing? No, yeah, that thing.
Anyways, I write it here. So x bar minus y bar minus mean divided something called S sub p, which is pooled standard deviation, times 1 and 1 and 1 and 2. This thing follows a t, basically follows a t distribution with these degrees of freedom. Okay? So, and the degrees of freedom is n1 plus n2, which is the sample size of the first population, sample size of for the second population, minus 2. So what is this SP? As you can see, SP is something like this. Okay? So it's the weighted average of estimate of the variances. So what I mean by that, let's use this sample and find or estimate the variance, which is S1 squared. Use this sample and find S2 squared, which is the variance estimate for the variance of second population. But here I have very good, an important assumption. They are equal. Since they are equal, I need to only estimate one element. Okay? So I can combine these two estimates. Okay? How I can combine them? Using weighted average. Because I know, let's say I have 5 observations here, 10 observations here. The variance I get here should be different from the variance I get here. Because I'm using only 5 observations, I'm using 10 observations here. So I need to use the sample size as weight. Okay? That's why, as you can see, let me write it down. I use a weighted average of these two, and I use sample size minus 1 as the weight. N1 plus N2, or let me write it down like this, because this is a weighted average, I need to add up the weights. Okay? Which is N1 plus N2 minus 2. Does it make sense? And that's the estimate. Okay? I use it here. Is it clear? And that's, I'm sorry, that's pooled S squared or pooled estimate of variance, which is an estimator for this sigma squared. Okay? The variance of two populations which are the same. Go ahead.
S1 and S2 are equal?
No, they are not. Definitely not. I mean, in very rare case, could be difficult. I mean, equal, but no, not in general. Because there are estimate of one. There are two estimates of one thing, which is this guy. So S1 squared is estimating this guy. S2 squared is estimating this guy, but they are doing the estimation using different samples. Now the question is, why not combine everything together to have a better estimate or more accurate estimate? Go ahead.
Will those two different sample variances approach one another as your sample size increases?
Yes, that's correct.
So at some point they're essentially...
Yes, exactly. So when n goes to infinity, let's say, S1 squared converges to this guy, S2 squared converges to this guy, then, as you said, they are going to be equal. Any other questions?
there a, sorry.
Yeah, go ahead. And
I
then.
missed this, but this is only if you're subtracting the one from the other.
Yes, but if.
The distribution if you're subtracting one sample from the other.
Yes, this is for x bar minus y bar. But if you are just considering x bar, then we had this case before. It's a t distribution with n minus 1 degrees of freedom. Or y bar is going to be t distribution with n minus 2. I'm sorry, n2 minus 1 degrees of freedom. Yeah. Now the question is, what is this, basically the difference of these two distribution? You good? Okay. Any other questions? Is it clear? Okay, good. So how about the distribution of ratio of the sample variances? Okay. So if we have two independent samples, here we are talking about the difference of x bar and y bar. And here we want to basically find, let me write it down here, s1 squared over s2 squared. Okay? So basically we can show if I have some multipliers, so s1 squared divided by the corresponding variance, population variance, s2 squared divided by corresponding population variance, okay? Then this guy follows an F distribution with n minus 1 degrees of freedom and n2 minus 1 degrees of freedom, okay? And it's very easy to show that. Do you remember the definition of F distribution? How we can get F distribution? Remember that? We have, you said what? Chi squared divided by degrees of freedom, another chi squared divided by degrees of freedom. Remember? So if I have one chi squared with nu 1 degrees of freedom divided by nu 1, another chi squared with nu 2 degrees of freedom divided by nu 2, this is F distribution with nu 1 and nu 2 degrees of freedom. Okay? I'm going to do the same thing here. I'm just going to erase that part. Okay? So I know that n1 minus 1 is 1 squared divided by sigma 1 squared. What is this distribution? Chi squared with n1 minus 1 degrees of freedom. Agree? The same thing for the other population. It's chi squared with n2 minus 1 degrees of freedom. Okay? Then I want to create an F distribution. So what I do, this is a chi squared distribution divided by degrees of freedom, which is n1 minus 1. Okay? Here, the second one divided by, sigma 2 squared divided by n2 minus 1. I know that this is F with n1 minus 1 and n2 minus 1. We cannot. This is F with 2 degrees of freedom. Okay? Is it clear? Then I can, if I simplify these two, I exactly get this one. So basically that's the reason why this guy follows an F distribution with these 2 degrees of freedom. That's the way to show that. We are using the definition of F, which is 2 chi squared divided by degrees of freedom. That's the first chi squared. That's the second chi squared. Does it make sense? Any questions?
Is there a slide where we've shown that n1 minus 1 s1 squared over, yeah.
This
That's
one,
equal to chi.
yeah, actually, I kind of like proved it on Monday. So it's not on your slides, but I like wrote it down on the board. Yeah.
It's just an
And I
expansion
use.
of it.
Yeah, exactly. Exactly. Okay. So one example. Let's say you have this guy, which is the sample variance using these basically random sample from the first population, and the other one is sample variance S2 squared is a sample variance of the second sample from the second population. Now the question is, what is this probability? What is the probability of ratio of the sample variances greater than 2? Okay. I give you a couple of minutes work on that. So what you need to do, you need to try to sort of multiply by something to make a distribution that you know. In this case would be this guy. Anybody got a number? No numbers? So what is the first step? To what?
Multiply by sigma 2 squared over sigma 1 squared.
Exactly. So what we want to do is to create this guy. So we multiply both sides by this guy. In this case would be 2 times what? Sigma 2 squared is 16. Sigma 1 squared is 4. So this gives me 1 squared divided by sigma 1 squared is 2 squared divided by sigma 2 squared. And this would be 8. So what I'm trying to do, I'm trying to create this guy because I know this distribution. It is F. Okay? Is it clear? How I did that? By multiplying the ratio of the population variance. Population variances. Any questions so far?
Do you know the N1 and the N2? Like,
We already have it here. That's actually a good point. X1 to X3, so N is 3. Oh, that's the tricky part. Yeah. And Y1 to Y3. So our N1 is equal to N2 is equal to 3 because we have X1, X2, X3, Y1, Y2, Y3. And they are independent. The independency assumption is very important. So this guy would be F with 2 and 2 degrees of freedom. Okay? Because the sample size is 3 for both of them. Any questions so far? So what is the next step? Use table? Everybody agrees? No. That's a special case, exactly. You cannot find this probably in table. I don't know. Can you? No. But it's a special case. We know that F2 and 2 is integrable. So what I'm going to do, I'm going to basically integrate the PDF function for F from A to infinity. So what is this PDF function? I just want to remind you right here is this guy. This is for F2 and 2. This is the PDF of F with 2 and 2 degrees of freedom. So we need to integrate this, which is this. And at the end of the day, I get 1 over 9. Okay? Any questions? Is it clear? I guess they cannot see it. Yep. Okay. A little bit. Okay.
In the equation you used, the smaller f, that was the PDF function.
This one?
Yeah, then you made that into 1 over 1 plus f.
Yeah, that's the PDF function, exactly.
Okay.
So that's the PDF function. You can use x. I just used f because it's f distribution. You can say g of x is 1 over x squared. That's it. The reason I used f because it's f distribution. That's it. Any other questions? You good? Okay. So one slide summarizing everything. Okay. One population, distribution of X bar or sample mean when you know the variance. What is it? Should be? Again, one population, X bar distribution when sigma is known. What is it? Normal. What if we don't know the variance? It would be T distribution with n minus 1 degrees of freedom. So one population, distribution of X bar, variance is unknown. So one population, distribution of S squared. What is it? Chi squared with n minus 1 degrees of freedom. Two populations, variances are known, and we want to know the distribution of X bar 1 minus X bar 2, or the distribution of difference in sample means. What is it? Normal. What if the variances are not known? Again, T with n1 plus n2 minus 1, n2 minus 2 degrees of freedom. What is the main assumption here? By the way, sigma 1 and sigma 2 are equal. And this is for the case that we want to know what is the ratio of the sample variances. Follows an F distribution. Okay? Go ahead.
I think it's usually the case that we don't know the population, the real sigma, and we know this S. So what is used for the F distribution? That's we are assuming that we know the sigma when we're getting the F distribution.
Oh, I see what you mean. So you will see later when we are having some confidence interval for the ratio of sigma 1 and sigma 2, then we use that F distribution.
Oh, so
and in
we
that
know
case,
S.
yeah, we know S because S is from sample.
Okay, I see.
We don't know sigma 1 and sigma 2, okay? So in some cases, you want to have some confidence interval or some interval estimate for the ratio of the variances.
And that's
Then you use F distribution, yeah. So we are going to use all these basic, these are the building blocks. We are going to use it later on for apply the stuff. Go ahead.
What does sample mean on this chart? Like,
Sample mean is X bar.
okay,
So this is sample mean.
so you would solve these equations for like X bar, I guess, kind of.
No, actually, we want to know what is the distribution of X bar. That's what it's trying to say.
The distribution of sample mean.
Exactly. So what is the distribution of X bar? What is the distribution of S squared?
Okay.
That's what we call like sampling distributions. Okay? Any other questions? You good? Okay. So 2 examples. We have 2 independent samples, x1 to xn, y1 to yn. We have basically 2 statistics, which are A and B. We want to find the distribution of A and distribution of B based on what you have. Give you a couple of minutes to work on it. Actually, let's make it more exciting. How about have it as a quiz? So it's open note and have a group quiz. What I mean by that, group of 2 work together on that problems, both A and B. Okay? So find a partner, work on it, A and B, maybe 10 minutes. Okay? So each group gives me 1 paper, okay, with 2 names. So do not have separate papers.
Professor, do you care if we have a group of 3 here?
No, 2 would be better. Are you looking for somebody? Yep, right here.
Yeah, but you have to divide this by something to get it. And minus 1. Okay.
Group of 2, only group of 2.
Yes, it's totally different. I mean, here is the small x, that is the big x. The sampling variable is for the, it's for the variables inside the big x. It's like sample, one sample. All the small x's are the variables. Oh, I see. Yeah, big x.
Plus. Yeah, so I was trying to say, like, yeah, where the
Group of two. Part A and B, yes, both of them.
No,
Guys, group of two, not group of two. Oh yeah.
the gravity for two populations in the energy. No, but the sigma remains.
So I think with these, you have some GI squared minus 3 plus
Chi squared separate. Yes, chi s equals
no, it's still A.
I'm sorry. I will write it down again.
So then what was the variance that simple variance? You said it was x small x.
Yes, so this is what the variance is for A.
Isn't this the same thing? It's the sample from population. This is for one sample. I think it's changed just like sample variance is different than okay. So this is for the data one sample. The next one? All the x1, xi. I've tried that before. So you mean there's just do one xi contains small xi, x1, x2, x2, like this? Is what you're saying? Yeah. This is what I'm thinking about. Yeah. Then it was your current Are the ends the same?
Yeah. Ends are the same. They're coming from same distribution. Okay. The distribution of two populations are the same. Both of them mu and sigma squared.
Here's the xi. Yeah. Yeah, it's always that's going to make it that.
What a chi
Okay, first of all, this is a chi square, but this is not standard normal. This is just for if you want to do this, if you want to convert this, we have to take mu out of it and then divide it by this to make it into standard. Then we can convert it to
No.
Oh, that's actually, yeah. Then we have. No, I think for the single sample.
5 minutes left.
It doesn't have any distribution actually. No, actually it follows. It has the no, it follows. I mean the population of this original population follows normal distribution, but it's not the same. What should our answer be? Like one of the distributions?
Yep, exactly. Is it normal, f, chi-squared t, anything? What is it? No, with the degrees of freedom. Yeah, distribution with the degrees of freedom. So for example, it is, no, it's not like that. So this is a random variable. At the end of the day, you want to see what is the distribution. Let's say, for example, is t distribution with n minus 1 degrees of freedom. That's it. That's it. There is no probability to calculate. There is no, yeah. Yeah.
We have two populations.
Huh? Go there. Okay. Thank you. You have your names, both of you? Yeah, okay, good. Thank you. Look at B again. Yeah. And how did you get 2? Yep, done. Thank you. Good. Thank you. Yeah. Thank you. Hmm. Okay. Oh. You know what? That's a good question. So the difference between variances, okay, negative number. You know, so a negative number for f distribution, for example, is not there. You know what I mean? So it doesn't mean that you cannot do that, but exactly. And the thing is, if you want to do that, you can do it for the log. You know what I mean? Log of sigma 1 minus log of sigma 2. And that's why if you signal to noise ratio, stuff like that, they have some log. I don't know, like, what is your background? Computer science. Okay. Yeah. So they have something like that also where they use log. Because if you take a log of ratio, then it's going to be, no, actually it's going to be the difference of the logs. Then they do that sometimes. If they want, they are interested in basically the difference between the variances. They do it in the log way. Okay. For the mean, exactly. And the mean could be negative, that's fine. For example, one is greater than the other and it follows a normal distribution perfectly for t also, because t and normal, both of them are both positive and negative. But s1 squared minus s2 squared, it's not easy to calculate. Okay, so it's not a very good, nice form. But yes, you can do that. You can calculate. Yes, these are going to be used later on when we are talking about confidence intervals. So I think the first part of the course is absolutely mathematics. Then we are going to use these building blocks to basically say, okay, how we are going to use them, you know.
This is the
Okay, time's up. Time's up, and bring your papers. Anybody else? Thank you. You have your names? Let me see. Close. You have your names? Thank you. Okay, what else? Anybody else's? Thank you. Thank you. Thank you. Okay, sure. Thank you. I got all the papers. Anybody else? Oh. Okay. So are you guys rewriting it? What are you doing? Just that's fine. You can do it later, but just give it to me. I have the. You don't have your names actually. Yeah, you do. Okay, good. So let's see. We have x1 to xn, NID, mu sigma squared. The same distribution for the second population with the same sample size. First one, actually the key information that you should know for solving both A and B is the definition of S squared. Okay? So S squared is summation of, let's call this one S1 squared, xi minus x bar squared n minus 1. Okay? That's the only thing that you need to know. Because for part A, what I'm going to do, I'm going to replace the numerator, which I'm using here in part A, if you look at part A. So this part, and I call it n1 minus 1, or actually, because both of them are the same, n minus 1 is 1 squared. Okay? How about the second one? N minus 1 is 2 squared. Okay? That's basically because summation of xi minus x bar, I just multiply these two. It's n minus 1 times s1 squared. Similarly for y's, and then divided by sigma squared. So I'm going to separate that. So this is equal to n minus 1 s1 squared sigma squared plus n minus 1 s2 squared sigma squared. Is it clear so far? So what is the distribution of this guy? It's chi-square with n minus 1 degrees of freedom. What is the distribution of this guy? Chi-squared with n minus 1 degrees of freedom. They are independent. Summation of two independent chi-square distribution again is chi-square distribution. So everything together is chi-square distribution with n minus 1 plus n minus 1 degrees of freedom. That's it. Now you see how easy was that. Okay? Any questions? What is it? Oh, if I do remember, there was a fact saying if you have chi-squared basically with nu 1 degrees of freedom, you have another chi-squared with nu 2 degrees of freedom, and they are independent. This follows a chi-squared with nu1 plus nu2 degrees of freedom. Just summation of the degrees of freedom. That was basically the fact that we had about summation of some chi-squares. Okay? It was in the review of probability, basically, lecture notes. Any questions so far? Is it clear? So that's the degrees of freedom for the first one. That's the degrees of freedom for the second one. So we add them up. Let's see part B. For part B, we have summation of xi minus x bar squared divided by summation of yi minus y bar squared. Again, I'm going to do the same thing. I'm going to use the same, basically, definition of S1 squared. So this would be this guy. This is n minus 1 is 2 squared. Okay? So simplify these two. What I'm going to do, both numerator and denominator, I divided by their corresponding variances, and their corresponding variances are the same. Why? Because I want to create an F distribution. Because this is the ratio of S1 and S2, so the ratio of S1 and S2 probably related to F. So if I do that, then it follows the F distribution with n1 minus 1 degrees of freedom, n minus 1 degrees of freedom, and n minus 1 degrees of freedom. Why? Because this has, the sample size for this guy is n, the sample size for this guy is n. Okay? And you know what? Since both numerator and denominator are divided by the same quantity, it doesn't change my ratio. Okay? Is it clear? Any questions? Actually, we have only 2 minutes left, so I guess I give you that 2 minutes. We can earlier. On Friday, basically, we are going to talk about estimations and the properties. So basically, if you have a random sample, how to use this basically random sample to estimate your parameter. And sometimes you could have different estimations. For example, for the mean, you can have x bar, or you can have mode, or you can have basically median. Okay? Which one is better and why is better? Now you have 1 minute. Go ahead.